Welcome to This Explainer. Today, we're tracking a literal hero's journey, the journey of a single network packet traveling through the dark, totally invisible space of a Kubernetes cluster. We so often take cluster networking for granted, kind of treating it like magic. But today, we're going to illuminate exactly what's happening under the hood. Picture this. You've got pods spinning up and dying every single second. IP addresses are completely ephemeral. So in that kind of chaos, how on earth does your front-end application actually find its back-end service? To solve this ultimate matchmaking challenge of dynamic IPs, we really have to look closely at the invisible mechanics of DNS. Section 1. The Dynamic IP Challenge. Why hard-coded IPs fail. Let's zoom right down into a cluster node and see how these containers are trying to communicate. Section 2. Inside the pod config. Discovering the local rules. To really grasp this, we need to step directly inside the front-end pod's local environment. Okay, so when you spin up a pod, Kubernetes quietly drops in a specific file, /etc/resolv.conf. If you were to check this file out, you'd find a meticulously defined local rulebook, including your search paths and this absolutely crucial setting called ndots. Right, so let's break that setting down. ndots 5 is a DNS threshold. Basically, it forces the system to treat literally any queried name that has fewer than 5 dots as an incomplete name. And because the system assumes it's incomplete, it triggers the sequential fallback, where it appends your local cluster domains first, way before it ever tries to reach out to the public internet. Section 3, the cascading fallback effect. Local versus public lookup. Let's see what happens when we put this rulebook to the test with real network traffic. Imagine our front-end pod, sitting in the production namespace, simply asks for backend. Well, the word backend has 0 dots. Since 0 is obviously less than 5, that ndots rule instantly kicks in. The system grabs the first local search path, stamps it right onto the packet, and suddenly it's backend.production.svc.cluster.local. Boom! For our internal service, that's an instant match. Now, that perfectly illustrates the cascade effect, but it also exposes a massive hidden trap. For internal stuff, sure, the match succeeds immediately. But what if your pod tries to reach an external API, say api.github.com? That URL only has 2 dots. 2 is less than 5, so the system is literally forced to fail sequentially through all of your local cluster domain paths first, before finally giving up and querying the internet. Section 4, hitting the CoreDNS hub, the network's authoritative truth. So, where does our successfully stamped packet actually go next? Well, our packet, now fully named, flies across the virtual network interface, striking the kubeDNS service IP like a bullseye. This is usually something like 10.96.0.10, routing directly into a CoreDNS pod instance, which is essentially the grand resolution help for the whole cluster. Inside that CoreDNS pod, it's sitting on a blazingly fast in-memory map. This map is continuously synced and updated by the Kubernetes API server itself. So CoreDNS, acting as the authoritative truth, queries this map and instantly translates our generated domain name into a reliable, stable cluster IP that the network can actually route to. Finally, Section 5, FQDNs and best practices, optimizing your DNS queries. Now that we understand this internal journey, how do we make it faster? The absolute secret weapon here is using a fully qualified domain name, or FQDN. This is just an absolute domain name formatted with a tiny yet incredibly powerful trailing dot at the very end, like api.github.com. By explicitly putting that trailing dot right in your application code, you are commanding the cluster to completely bypass those ndot sequential search paths. Why does one little dot matter so much? 4. That's the number of entirely unnecessary network round trips you save simply by using FQDNs for your external resources. Instead of firing off useless queries that inevitably fail against your local network, your application bypasses the nonsense and goes straight to the internet, instantly. Which brings us to a really vital takeaway. Visualizing the invisible mechanics of DNS is the difference between running a functional cluster and a blazingly performant one. Once you grasp this micro journey, the resolv.conf, that tricky ndots threshold, the CoreDNS map, you completely stop treating cluster networking like some magical black box. So I have to leave you with a critical question about your own architecture. Are your external API calls secretly burning precious milliseconds right now, silently failing through local search domains? I highly encourage you to go check your pod's resolv.conf today. Uncover that hidden latency living in your cluster and ask yourself, is a single missing dot slowing down your entire application?